In this video, we'll talk about the damped force oscillator. The first topic we'll go over is, first of all, how to produce the mathematical solution for the damped case. Remember, the damping term is this frictional term on the motion of, for example, a mass on a spring. And of course, it's forced by, in this case, in the example we'll go through, it's forced by a oscillating function with frequency omega, capital omega, as a function of time. So we'll first derive the solution, the particular solution or the non-homogeneous solution, as well, and remind ourselves about the homogeneous solution. And then we'll examine the behavior of the system for different values of this damping coefficient, C right here. So your personal sort of learning objectives is you'll be able to find the general solution for this system. And then, as importantly, you'll be able to relate the solution and the behavior of the solution to the physical processes being mathematically modeled. This is section 3.8.2 of Greenberg. It's the damped oscillator. And I'll go ahead and write down this equation again. Remember, we have a mass, for example, on a spring, and it's this the x double prime is the acceleration term, so this is mass times acceleration, plus the viscous, what we're calling the damping term. It's the viscous resistance of the mass to motion. And then we have the spring constant times the displacement of the spring. X is always the displacement of the spring. And then we're driving it, we're pulling on the mass with a force of amplitude F naught, and it's a oscillating function or harmonic function with driving frequency capital omega. So now we have a non-homogeneous equation. So we have to find the particular solution, and to do that we realize first that we check to see that the coefficients are constant, and indeed m, c, and k are constant. And then we have to make sure that the family of linearly independent functions, when we take derivatives of the forcing function, is finite. There's a finite set. And indeed, as we take derivatives of cosine omega t, we'll get sines and cosines. And that is the Li family of this function is cosine omega t and sine capital omega t. And so we therefore know that we'll tentatively check to see whether we'll tentatively assert that the non-homogeneous solution is a linear combination of cosine and sine omega t. And the next step is to look at the homogeneous solution. So xh is the homogeneous solution. And it is of the form e to the lambda t, because remember we have a case of constant coefficients. And therefore, when we substitute e to the lambda t into our original equation, we get the characteristic equation, m lambda squared plus c lambda plus k is equal to 0. And this tells us, using the quadratic equation, that lambda is equal to minus c plus and minus the square root of c squared minus 4mk all over 2. And I'm reviewing this because for the homogeneous solution, what the behavior was very different depending on what was under the square root here. So there, and I'll remind you that we had a critical damping value, CR, which equals 4mk. Okay, so there were 3 cases that we looked at, 3 cases or 3 types of solutions or 3 behaviors of solutions. So when C is less than this critical value, then we called this underdamping. And when C squared is less than minus 4, sorry, the critical damping is, so the critical damping squared is 4mk. So the critical damping itself is the square root of 4mk. So when C squared is less than 4mk, then what's under the square root is negative, and lambda is imaginary. And that gives a term y sub h is proportional to e to the I t, and we get, and well, more specifically, let me go ahead and write that out. We get an oscillatory behavior. So y sub h is equal to e to the minus c over 2mt a cosine times the square root of omega squared minus c squared over 4m squared times t plus b sine that same term, that same function of t. So that was the first case in which we have underdamping. For the second case, where C is equal to this critical damping value, the square root of 4mk, then we get critical damping. And the solution for the homogeneous part is y is equal to, again, we see this exponential decay term, but we don't get oscillation, we just get a linear function with critical damping. And then the last case was when C is greater than the critical damping value, and this is what we called overdamping. And we get y sub h is equal to, again, our exponential decay, c e raised to the minus c over 2m times t, and then we get our hyperbolic functions, because lambda is all, what's under the square root is positive, but we get 2 distinct solutions, and those give the Cosh functions, or the hyperbolic functions, I should say. So those are our 3 cases. So now that we know the possible range of homogeneous solutions, we need to see if there's any redundancy between our non-homogeneous solution and our homogeneous solution. And in fact, there is no redundancy, even when, for example, um, little omega is equal to big omega. Remember, with the underdamped case, um, or sorry, without damping, we ran into the situation when big omega was equal to little omega, little omega being the driving frequency. I'm sorry, the natural frequency of the spring. When those two were equal, we got resonance. But even in this situation, since we have damping, this exponential decay term makes all of the solutions, all of the parts of the homogeneous solution, linearly independent from the two harmonic functions describing the non-homogeneous solution. So again, there's no duplication between the non-homogeneous solution and the homogeneous solution because of our damping term. And so this describes our full non-homogeneous solution. And so we now just have to solve for our coefficients. And we do that by substituting this into our original equation, isolating like terms, and then solving for C and D. So again, we put X non-homogeneous into our ODE and solve for C and D, our undetermined coefficients. And we'll find, so I'll just write this down again. And so we'll find that C and D, oops, I'm just noticing I wrote B above here. We're solving for C and D, are functions. They're constants, but they're functions of the constants F naught, our driving force, divided by, or the magnitude of our driving force divided by the mass, our damping coefficient, and our natural frequency, as well as our driving frequency. And we can then rewrite this into a single harmonic function. We can rewrite this in terms of E cosine capital omega t plus phi. So our two constant C and D are now related to the new constants E and phi. And E and phi is, so where E is equal to the magnitude of our driving force divided by m all over the square root of little omega squared minus big omega squared times 2, or squared, times c big omega over m squared. And capital phi is equal to the arctangent, the inverse tangent of c omega m over capital omega squared minus little omega squared. And with this definition, phi will always, well, it's sort of understood that phi is in the range of 0 and pi. And just to remind you, the natural frequency is omega, and that's equal to the square root of k over m. So the larger k is, the stiffer the spring is, and the more quickly the mass will tend to oscillate. And of course, the more massive the object is, that will tend to resist the oscillation by inertia. And so that's why m is in the denominator here. So just to remind you of these different terms. So just to highlight the homogeneous solution, the non-homogeneous solution is a cosine function, just as the driving force was. So it's a cosine function, and remember the driving frequency was capital omega, and the response is also has a frequency of capital omega, but there's a phase shift to this. So the homogeneous solution again is a let me draw a cosine function. So I'm gonna draw the homogeneous solution as the non-homogeneous solution, the particular solution, as a function of time, and it's a cosine function, but that has a phase shift on it. Let's see if I can sketch this reasonably well here. Okay, that's okay. And so the phase shift is capital phi, and I'm noticing I should have drawn a capital phi here, not a lowercase phi, plus capital phi. Please correct this in your notes. Right, we have capital phi given right there. And so this is a phase shift, phi, and of course the period here is given by the time between two peaks, and the driving frequency is 2 pi over the period. So this is the homogeneous solution. Now let's look at the magnitude of the oscillation, and this is given by E. So this is the magnitude, or I should say amplitude of the oscillation. And Greenberg shows a nice plot of this amplitude, and let me go ahead and rewrite it here just so we'll see what it looks like. So again, E is equal to F naught over M all over the square root of little omega squared minus big omega squared all squared plus C big omega over M squared. And let me see if I can sort of reproduce Greenberg's figure here. So we're going to show how the amplitude depends on the driving frequency, capital omega. So this is amplitude E. And you may not be surprised if you remember what happens in resonance when capital omega is equal to little omega, then the amplitude is infinite. So the amplitude increases when big omega is less than little omega. It increases as big omega approaches little omega, and it goes on to infinity here. And then on the other side, it decays to 0. And so that's when this occurs, when C is equal to 0, right? When C is equal to 0, we looked at the case when, well, there's no damping, and we can have a resonance when the driving frequency equals the natural frequency. When C is equal to the critical value, then the amplitude is largest as capital omega approaches 0, and then it decreases as capital omega increases. And then finally we have a I guess supercritical damping when C is greater than the critical value here. And I'd also like to point out that if C is small but still non-zero, you can get solutions that have peaks in amplitude near when capital omega is near lowercase omega, and it looks something like this. So the amplitude of the oscillation that's driven by the forcing function depends on how large capital omega is, and it also depends on how strong the viscous damping is to the system. So the total solution is then the homogeneous solution plus the particular solution, or the non-homogeneous solution. And just to remind you, we have the homogeneous solution always has an exponential decay with time, and we had, remember, we had the 3 cases depending on how large C was, and then we have our oscillating non-homogeneous solution. So this is oscillating with frequency equal to the driving frequency, and this is our exponential decaying function. And if you recall, when we looked at the linear situation, we looked at an LR circuit. We found that the homogeneous solution led to an exponential decay with time, whereas the particular solution in the example that we looked at led to a non-decaying function with time. And in that case, it was constant. So, so the results are quite analogous in this case as well for the higher order ODE. So, so that wraps up this video on a damped force oscillator, which relates to a higher order ODE with constant coefficients.